In this video for our NMR lecture, we'll be looking at the peak splitting in our NMR spectrum. Spin-spin splitting indicates the number of neighboring hydrogens in our NMR spectrum. This can be explained using the N+1 rule. Each type of proton senses the number of neighboring protons bonded to the neighboring carbon, and its resonant peak is split into the N+1 components. Some examples of our NMR peaks here is a singlet, a doublet, a triplet, quartet, quintet, sextet, and septet. The name we give to the peak indicates how many times it got split. So a singlet got split 0 times. A doublet got split once, a triplet got split twice, and so forth and so forth. And if we look at the heights of our peaks, we can see that they follow a pattern. If you recall from your math classes, the pattern it follows is known as the Pascal triangle, where your central peak is always going to be your tallest, and then it goes down to smaller peaks from there. Once we get towards the septet region, you can see those peaks at the very end tend to be really small compared to your central peak. Let's look a little closer at this N+1 rule. So looking at the N+1 rule, when n equals 0, the n+1 is 1. So we have 0 plus 1 gives us 1, which means we have a singlet. If n, so if our neighboring carbon has 1 hydrogen, then we'll see 2 peaks. So this would be a carbon with a single hydrogen on it, and then it'll be bonded to 3 other things. If our carbon has 2 hydrogens, so if we have a CH2, that'll give us a triplet. If we have a CH3, that'll give us a quartet. Now, when you have 4, 5, or 6 neighbors, that means if we're looking at our central carbon here with its hydrogen, it'll have to be bonded to 2 other carbons at least. So there might be 2 hydrogens on this side and 2 hydrogens on that side. That would give us 4 neighbors. We can think of the same pattern to give us 5 or 6 neighbors. One important thing when we're talking about neighbors is our atoms are usually 3 bonds apart. What that means is if we're looking at this hydrogen, then it'd be 1, 2, 3 bonds to the next hydrogen. If, let's say, we have another carbon here and then another hydrogen, that would be 3, 4 bonds. 4 bonds do not show peaks typically. It's typically 3 bonds apart. So some common features in the splitting of our NMR. The most common coupling occurs between those 3 bonds. So it'd be 1, 2, 3. Ones that are 4 bonds apart generally do not show coupling. There are some exceptions, but generally they do not. Coupling is not observed through oxygen or hydrogen. So that means if I have a carbon with a hydrogen and it's connected to an OH, that may be 3 bonds apart, but it does not show any coupling. Chemically equivalent hydrogens also do not couple. So if I have a carbon that has multiple hydrogens on it, if I have a methyl group, for example, those hydrogens from the methyl group do not couple to each other. And then finally, coupling is observed through protons that are separated by 2 bonds only if they are chemically distinct. This typically happens when we have protons attached to a double bond. These 2 protons are chemically distinct from each other, since a double bond, as we know, does not rotate. So looking at a couple examples and practicing our splitting patterns. We can see our spectra here. I've given you the structure. The structure is ethanol. Now if we look, I have an OH, a CH3, and a CH2. If we first look at a CH3, the CH3 is bonded to the CH2. That CH2 has 2 hydrogens. So that means my CH3 has 2 neighbors. If it has 2 neighbors, it's going to show 3 peaks in the NMR. 3 peaks is a triplet. So then we look on our spectra, and we see right here, we have 3 peaks. So that means that has to be my CH3. Then next we look at the CH2. My CH2, it's bonded to the OH, but that does not couple. My CH3, it does couple. So for the CH2, we have 3 neighbors, which gives us 4 peaks, which means we have a quartet. And we can see that's right here in the NMR spectrum. And our last one is going to be the OH. Remember, OHs and NHs typically do not split. So that'll show up as a singlet. So this is how we can go through our NMR spectrum to try to figure out our splitting patterns. I'll look at one last example of isopropanol. Looking at these 3 peaks, we can see we have a few things. We have a singlet where I've designated as 1. At 2, we have 1, 2, 3, 4, 5, 6, 7 peaks. You can see the 2 on the very end become hard to see sometimes. And then the peak I've designated number 3, we can see it's a doublet. So looking at our compound, if we're to draw out the Lewis structure, we'd see there's a hydrogen in the middle there that's not shown in the line structure. And then I have my CH3 methyl groups. So examining this NMR, first I can tell that the OH, it's going to be a singlet. So my OH group here will be what I designate as hydrogen 1. Be that peak. Now we need to figure out the carbon-hydrogen peaks. If I think about my methyl groups are equivalent to each other. Since they are equivalent, they will show up as a single signal in the NMR spectra. And then looking at my CH3 groups, they have 1 neighbor, that's CH. So since they have 1 neighbor, they will give me N+1 signals. N+1 signals means I will see 2 peaks or split into 2 peaks in the NMR spectra. So that will be a doublet. Which means this signal close to 1 has to be both of the CH3 groups. And then finally, my single CH group. That CH group has 6 neighbors. Since it has 6 neighbors, we have to count it as 7 peaks. So 7 peaks was our septet. Now note, when we're counting the neighbors, we count each of the CH3 groups. We count the total number of neighbors, not just the equivalent type, the total number. So that's how we get this peak here, or that peak gets split into 7 peaks. So you can see this is an example here where we have a larger number of neighboring protons. Each of those hydrogens on the methyl groups are 3 bonds away from that CH group circled in green. You can see by looking at the splitting pattern, we're able to start figuring out the number of neighbors, which means I can start drawing pieces to my molecule.